Bismuth oxide is perhaps the most industrially important compound of bismuth. It is also a common starting point for bismuth chemistry. It is found naturally as the mineral bismite and sphaerobismoite, but it is usually obtained as a byproduct of the smelting of copper and lead ores. Bismuth trioxide is commonly used to produce the dragon's eggs effect in fireworks, as a replacement of red lead. Structure. The structures adopted by bismuth trioxide differ substantially from those of arsenic oxide as 2O3 and antimony oxide, antimony trioxide. Bismuth oxide. Bismuth trioxide has 5 crystallographic polymorphs. The room temperature phase alpha-bismuth trioxide has a monoclinic crystal structure. There are 3 high-temperature phases: a tetragonal beta phase, a body-centered cubic gamma phase, a cubic delta bismuth trioxide phase, and an epsilon phase. The room temperature alpha phase has a complex structure with layers of oxygen atoms with layers of bismuth atoms between them. The bismuth atoms are in 2 different environments which can be described as distorted 6 and 5 coordinate respectively. Beta bismuth trioxide has a structure related to fluorite. Gamma bismuth trioxide has a structure related to that of bi12 silicon peroxide, where a fraction of the biatoms occupy the position occupied by SiIV, and may be written as bi12 by 0.8019.2. Delta bismuth trioxide has a defective fluorite-type crystal structure in which 2 of the 8 oxygen sites in the unit cell are vacant. Epsilon bismuth trioxide has a structure related to the alpha and beta phases, but as the structure is fully ordered, it is an ionic insulator. It can be prepared by hydrothermal means and transforms to the alpha phase at 400 degrees Celsius. The monoclinic alpha phase transforms to the cubic delta bismuth trioxide when heated above 729 degrees Celsius, which remains the structure until the melting point, 824 degrees Celsius, is reached. The behavior of bismuth trioxide on cooling from the delta phase is more complex, with the possible formation of 2 intermediate metastable phases: the tetragonal beta phase at the body-centered cubic gamma phase. The gamma phase can exist at room temperature with very slow cooling rates, but alpha-bismuth trioxide always forms on cooling the beta phase. Even though when formed by heat, it reverts to alpha-bismuth trioxide when the temperature drops back below 727 degrees Celsius. Delta-bismuth trioxide can be formed directly through electrodeposition and remain relatively stable at room temperature. In an electrolyte of bismuth compounds that is also rich in sodium or potassium hydroxide so as to have a pH near 14. Conductivity. The alpha phase exhibits p-type electronic conductivity at room temperature, which transforms to n-type conductivity between 550 degrees Celsius and 650 degrees Celsius, depending on the oxygen partial pressure. The conductivity in the beta, gamma and delta phases is predominantly ionic, with oxide ions being the main charge carrier. Of these, delta bismuth trioxide has the highest reported conductivity. At 750 degrees Celsius, the conductivity of delta bismuth trioxide is typically about 1 ScM-1, about 3 orders of magnitude greater than the intermediate phases and 4 orders greater than the monoclinic phase. The conductivity in the beta, gamma and delta phases is predominantly ionic, with oxide ions being the main charge carrier. Delta bismuth trioxide has a defective fluorite-type crystal crystal structure in which 2 of the 8 oxygen sites in the unit cell are vacant. These intrinsic vacancies are highly mobile due to the high polarizability of the cation sublattice with the 6s2 lone pair electrons of Bi3+. The bio bonds have covalent bond character and therefore weaker than purely ionic bonds, so the oxygen ions can jump into vacancies more freely. The arrangement of oxygen atoms within the unit cell of Bismuth Trioxide has been the subject of much debate in the past. 3 different models have been proposed. Silene used powder X-ray diffraction on quenched samples and reported the structure of Bismuth Trioxide was a simple cubic phase with oxygen vacancies ordered along an LT 111 and GT-IE along the cube body diagonal. Gatow and Schroeder rejected this model, preferring to describe each oxygen site in the unit cell as having 75% occupancy. In other words, the 6 oxygen atoms are randomly distributed over the 8 possible oxygen sites in the unit cell. Currently, most experts seem to favor the latter description, as a completely disordered oxygen sublattice accounts for the high conductivity in a better way. Willis used neutron diffraction to study the fluorite system. He determined that it could not be described by the ideal fluorite crystal structure. Rather, the fluorine atoms were displaced from regular 8C positions towards the centers of the interstitial positions. Schuck et al. And Sams et al. Suggest that because of the high degree of disorder in Bismuth Trioxide, the Willis model could also be used to describe its structure. Used in solid oxide fuel cells, interest has centered on Bismuth Trioxide as it is principally an ionic conductor. In addition to electrical properties, thermal expansion properties are very important when considering possible applications for solid electrolytes. High thermal expansion coefficients represent large dimensional variations under heating and cooling, which would limit the performance of an electrolyte. The transition from the high-temperature Bismuth Trioxide to the intermediate Bismuth Trioxide is accompanied by a large volume change and consequently, a deterioration of the mechanical properties of the material. This, combined with the very narrow stability range of the delta phase, has led to studies on its stabilization to room temperature. Bismuth Trioxide easily forms solid solutions with many other metal oxides. These dope systems exhibit a complex array of structures and properties dependent on the type of dopant, the dopant concentration and the thermal history of the sample. The most widely studied systems are those involving rare earth metal oxides, Lane 203, including yttria, Y203. Rare earth metal cations are generally very stable, have similar chemical properties to one another and are similar in size to Bi3+, which has a radius of 1.03 A, making them all excellent dopants. Furthermore, their ionic radii decrease fairly uniformly from La3+ through Nd3+, Gd3+, Dy3+, and Er3+ to Lu3+, making them useful to study the effect of dopant size on the stability of the Bismuth Trioxide phases. Bismuth Trioxide has also been used as sintering additive in the scandium oxide-doped zirconia system for intermediate temperature SOFC preparation. Bismuth trioxide is commercially made from bismuth subnitrate. The latter is produced by dissolving bismuth in hot nitric acid, addition of excess sodium hydroxide followed by continuous heating of the mixture precipitates bismuth oxide as a heavy yellow powder. Also, the trioxide can be prepared by ignition of bismuth hydroxide. Reactions. Oxidation with ammonium persulfate and dilute caustic soda gives bismuth tetroxide. The same product can be obtained by using other oxidizing agents such as potassium ferrocyanide and concentrated caustic potash solution. Electrolysis of bismuth oxide in hot concentrated alkali solution gives a scarlet red precipitate of bismuth oxide. Bismuth oxide reacts with mineral acids to give the corresponding bismuth salts. Reaction with acetic anhydride and oleic acid gives bismuth Trioxide. Medical device usage. Bismuth oxide is occasionally used in dental materials to make them more opaque to X-rays than the surrounding tooth structure. In particular, bismuth oxide has been used in hydraulic silicate cements, originally in MTA from 10 to 20% by mass with a mixture of mainly di- and tricalcium silicate powders. Such HSC is used for dental treatments such as apicoectomy, apexification, pulp capping, pulpotomy, pulp regeneration, internal repair of iatrogenic perforations, repair of resorption perforations, root canal sealing and obturation. MTA sets into a hard-filling material when mixed with water. Some resin-based materials also include an HSC with bismuth oxide. Problems have allegedly arisen with bismuth oxide because it is claimed not to be inert at high pH, specifically that it slows the setting of the HSC, but also over time can lose color by exposure to light, a reaction with other materials that may have been used in the tooth treatment, such as sodium hypochlorite.